So it is my esteemed and unmitigated pleasure to introduce our speaker for the 1W-MINDS seminar this Thursday, Dustin Mixon. He is an assistant professor at Ohio State University who does a lot of influential and I think personally very interesting work on a wide variety of problems in frame theory, signal processing, compressive sensing, and data science, which is what the talk will be about today, based, I presume, on the abstract. And if anyone watching wants to browse an interesting blog, you should go check out his short fat matrices blog that he keeps up. I believe there is a math prize there that you can win involving a bottle of whiskey, if I read correctly last time I looked. So it sounds exciting to me. So without any more ado, I will turn things over to Dustin to let us know what he's going to talk to us about today.
Great, thanks for the invitation. I'm going to be talking about some work that was supported by the National Science Foundation and the Air Force Office of Scientific Research. But first, I want to tell you a little bit about myself. The last couple of months, I've been spending time in my basement. This is my basement right here. I got that nice white pillar I get to look at whenever I do a Zoom call. And when I need to relax, I find myself consuming a lot of media on the internet. Maybe you're familiar with some of these. But I want to bring your attention to this guy right here. Hopefully you can see my mouse. This is Adam Ragusea. He used to be a journalism professor down in Georgia until he realized that he makes more money as a YouTuber teaching people how to cook from home. And you see he's holding a tomato there. I want to share with you something that I've learned by watching his channel. It turns out that ingredients matter. So let's talk about tomatoes. You can grow tomatoes in your backyard with a garden. And when you do that, you get to pick it when it's exactly ripe. And that makes it extremely flavorful. So you can make a caprese salad that tastes amazing. Alternatively, you could buy a tomato from the store. So these are store-bought tomatoes, and these are homegrown tomatoes. You can see the difference, and the taste is evident as well. You could attempt to make a caprese salad with a store-bought tomato, but the results won't be so good. Instead, you should probably go for like pico de gallo or something that has other ingredients that would allow it to taste really good. Finally, maybe you have a rotten tomato, something that went bad on you. You could attempt to salvage it and maybe make some chili. Maybe you would do that if you're a fast food restaurant. Maybe you shouldn't do that yourself. But the point is that if you have better ingredients, you're able to do a lot more. And it turns out that a similar thing happens in data science. Ingredients matter in data science. So for example, we're all familiar with how to solve a linear inverse problem. You have AX equals B, you want to solve for X. You can do that provided the rows of A are sufficiently different in some sense. In particular, if they span the space, then you can solve for X. More generally, if you have diverse data, then that will allow you to get identifiability. Another example, informative prior. This is a really nice ingredient. If you have a really informative prior, it tells you a lot about what you're expecting, then you can actually decrease the sample complexity. This is most notable in compressed sensing, where you can solve AX equals B even if the rows don't form a spanning set. You can have far fewer samples and able to recover X. Another ingredient that maybe we don't talk about too much is that if you have really strong signal, then the algorithm that you have to produce an estimate can probably be made faster. So if you have a stronger the signal is, the faster the estimation is. And one way to think about this is, imagine looking for a needle in a haystack. It's hard to find a needle in a haystack, but if it's mostly needles, or if you have a lot of needles, then there's a lot more signal. It's quicker to find that needle. Okay. In this talk, we're going to be looking at a few instances of ingredients mattering, and we'll be focusing on examples that come up with clusters and manifolds and epidemics. We'll start with clusters. Okay. This is joint work with my engineering PhD student, Kaiying Xie, and let's do this. So the problem we're interested in is minimum bisection in the stochastic block model. Some of you are probably familiar with this problem, but I'll reintroduce you anyways. So we have two planted communities of vertices. They're going to have the same size. Here they're blue, is one community, and the red vertices are another community. And then we're going to draw edges at random. Edges between vertices of a common color will be drawn with probability P, and an edge between vertices of different colors will be drawn with probability Q. So this is kind of a generalization of the Erdős-Rényi graph model. Okay. What we receive is not the graph with the vertices colored, but rather the vertices are all mixed up and the labels are removed. We don't see the labels. And our goal is to solve minimum bisection. In particular, we want to minimize the number of edges between S and S complement, where S is a subset of half the vertices. Okay, so which is the way to bisect the vertex set in a way that minimizes the number of edges going across the partition. So reasonable questions to ask here is, how do you actually find the optimizer? You could imagine this being a hard problem to solve in general, but how can one do it in the stochastic block model? And furthermore, when you solve minimum bisection, does it actually recover the communities that you're looking for? Okay. So one popular way of solving this problem is to relax to a semi-definite program. Let me explain how to do that. So we're going to encode our subset of vertices S as a vector X, where X is going to be 1 on S and -1 on S complement. The vector of plus minus ones, and the ones tell you what S is. So if you are interested in counting the number of edges between S and S complement, it turns out that that equals this expression in terms of the adjacency matrix and X. Okay, that's an easy identity. If you simplify that further, it takes the form of a constant minus a quarter of the inner product between the adjacency matrix and XX transpose. So if you're interested in solving minimum bisection, that corresponds to looking for the X for which this inner product is as big as possible. You can express, if you take XX transpose to be a matrix big X, then you can express the problem this way. So the constraints here are, I want the diagonal of X to be all ones, I want X to be positive semi-definite, and I want the rank to be 1. These three constraints ensure that big X takes the form XX transpose, where X is all plus ones and minus ones. And then this last constraint ensures that little x has half plus ones and half minus ones. That corresponds to us wanting a bisection. And then you can maximize, what we're doing is we're maximizing the inner product between A and X, but we can also modify the objective without changing anything. We can subtract some multiple of the all ones matrix, J. The reason this is okay is that 1 is in the null space of X. So X doesn't see this perturbation of A. The reason that perturbation is interesting is that when you relax to a semi-definite program, you end up with a different objective. So we're going to relax by throwing away this rank constraint as well as this x1 equals 0 constraint. And what we're left with is a semi-definite program that'll be different depending on what mu is. When mu is 1, this is known as the Gomans-Williamson semi-definite program. And when mu is a half, you get a semi-definite program that was specifically designed to help solve this minimum bisection problem under the stochastic block model. This was developed by Abe, Bandera, and Hall. So one nice thing about this semi-definite program is that it allows you to prove a theorem about exact recovery of the planted communities. We're going to be focusing on a certain regime. It kind of corresponds to the connectivity regime in the Erdős-Rényi graph model. We're going to let P and Q, these probabilities of edges, to scale like log n over n. And the scalar out front we're going to call alpha and beta. So the phase transition that occurs is if square root alpha minus square root beta is bigger than square root 2, then the semi-definite program exactly recovers the communities with high probability. On the flip side, the opposite inequality makes it so that with high probability, there is no algorithm that can identify the communities. This is a plot to illustrate this phase transition in a non-asymptotic setting. So here n is like 300, and darker means lower probability of recovery by the semi-definite program, and lighter means that semi-definite program recovers. And the red line here denotes the phase transition, root alpha minus root beta equaling root 2. So you can see that there's a stark contrast between these two regimes. And it's pretty impressive that the semi-definite program recovers all the way down to the information theoretic threshold. So one problem about semi-definite programs is that while they're good for clustering, not just graph clustering, we see them with k-means clustering and other clustering problems. They're really good for clustering, but they end up being slow to solve in practice. And this can be frustrating if you're ever trying to solve a semi-definite program. But there's this, this idea that ingredients matter. That's kind of the point of this talk. In this case, if we have more signal, we can maybe expect a speed up of sorts. It's like finding needles in a haystack. In general, I suspect that there's a meta theorem out there that clustering is easier when there's more signal. This is, in this particular case, we're interested in the regime when square root alpha minus square root beta is not just bigger than square root 2, it's much bigger than square root 2. So in this regime, you can kind of see something like a phase transition here. Like this curve right here corresponds to root alpha minus root beta equaling root 2. This is the runtime of the SDP. You throw it to CVX and you ask it to solve, and you tick-tock to find out how long it takes. So these darker regions, it takes 6 seconds, and these lighter regions appear to take on the order of 3 seconds. So you can see there's a slight dip in the runtime. But there's actually more that can be done here. A slight modification of the semi-definite program makes it so that you can get much faster runtimes. And that's what I'm going to be talking to you about. So the big idea is that this thing called sketch and solve. Sketch and solve is a way to solve problems in general. I give you a big problem, it's hard to solve. What you're going to do is you're going to randomly pass to a smaller problem. This is called sketching. So you pass to a smaller problem, and then once you reach this smaller problem, it's something that you can actually solve quickly because it's smaller. And once you solve that smaller problem, you're going to somehow use it to stitch together a solution or an approximate solution to the original problem. So you sketch down, you solve the sketch problem, and then you lift back up to find a solution to the original problem. Sketch and solve. So this has been successful for solving large least squares problems where the size of the data is too big to fit on a single machine. You can sketch down to a problem that you can actually solve and then lift up to an approximate solution overall. We're interested in clustering, and what we're going to find is when we have more signal, we can sketch down to an even smaller problem. Like the more signal we have, the further down we can sketch. And what that means is this step 2 is going to be faster. For us, step 2 amounts to solving a semi-definite program. And if you're solving that semi-definite program for a smaller matrix, it's going to take a lot less time. That's where our savings is going to come from. So 3 steps. The first step is to sketch. So here's an illustration of 2 communities, each with 16 vertices. And we're going to randomly select a subset of these vertices. Now, when we do this, we don't know what the communities are, right? If we knew what the communities are, we wouldn't have a problem to solve. So when we randomly select a subset of these vertices, we're not going to have control over how many vertices are selected from each community. So in this case, when we sketch down, we're looking at the induced subgraph of some random subcollection of vertices. And we end up with the red community is a little smaller than the blue community here. So that poses a question: how do we solve this exact recovery of communities problem when the communities aren't the same size? Well, that's what we're going to do in step 2. We're going to figure out how to recover unbalanced communities. And the algorithm is, it's going to be the same semi-definite program from before, where we have A minus mu j interproduct with x, and it's a semi-definite program because we relaxed away the rank constraint, and we also relaxed the x1 = 0 constraint. Okay, so this is our algorithm, and I'm going to show you how this algorithm performs in a special case where one of the communities is of size 100 and the other community is of size 200. So this is very unbalanced. So darker denotes failure and lighter denotes success. This is probabilities going from 0 to 1. And you can see that the Gomans-Williamson semi-definite program, that's when this mu = 1. It doesn't do nearly as well as what the Abbe-Bandera-Hall semi-definite program provides. So just by turning this knob, changing mu, you end up with a substantially different performance when the communities are not balanced. Okay, so this seems to be particular to the unbalanced case. So is mu = 1/2 the best possible? Well, we turned knobs and we observed that it's actually better to select mu to be dependent on the data, like dependent on these probabilities. So if mu = p plus q over 2, okay, so that means mu is different for each of these pixels, right? You have alpha and you have beta. P and q are determined by alpha and beta. This is the phase transition you get for this choice of mu. And you notice that it lines up really nicely with this red curve. If you could make that red curve out, it's pretty small here. This is square root alpha minus square root beta equals square root 2. So for some reason that we don't completely understand, the same phase transition is emerging in the unbalanced case when you select mu to be p plus q over 2. So we don't know how to estimate p plus q over 2 when we're given unbalanced communities, but we can estimate them when we're given a graph with balanced communities at the very beginning. So at the beginning, we're given a graph with balanced communities. We can just take the average degree of that original graph, and that'll be an estimate for p plus q over 2. So we can take that estimate and then sketch down and use that estimate as our choice of mu and expect decent performance. Okay. So step 3, we solve the original problem. So at this point, we've identified the community for the subset that we sketched down to. And now we want to figure out which communities these yellow vertices, the vertices that we threw away, what communities should they belong to? And it turns out that a simple voting is gonna do well. So for each vertex that isn't labeled yet, you ask his labeled neighbors, which label should he have, and majority rules. So overall, we start not with step 1 from sketch and solve. We actually start with step 0 here. We're going to estimate p plus q over 2 just by grabbing the average degree of the full graph. And then we pass to a random subgraph. This is the sketching by running a Bernoulli process. So the probability of keeping a vertex is gamma. So each gamma survives with probability gamma here. So once we've passed down to a induced subgraph, we'll run the semi-definite program with this particular choice of mu parameter to label the vertices in that subgraph. And then we hold a vote in the original graph to decide how to label the remaining vertices. And it works. So when alpha is much bigger than beta, so when you have lots of signal, you can afford to send gamma way down. The point of comparison is the original STP would take gamma to be 1, right? So whenever you take gamma to be smaller than 1, you can expect a savings in the solution. We suspect that this goes all the way down to this threshold. If you take gamma to equal 1 in this inequality and rearrange, you get square root alpha minus square root beta is bigger than square root 2. So we suspect that that phase transition is actually governing how small gamma can be taken to be. So open question, is that conjecture true? Also, in order to prove that our conjecture, you'd have to understand where this phase transition is coming from in the unbalanced case. Why does it appear to have square root alpha minus square root beta equaling 2 calling the shots? We'd like a principled method for selecting this hyperparameter gamma. At the moment, you can guess and check with by doubling gamma each time, but it'd be nice to have a principled technique here. We estimated p plus q over 2. We were able to do that because we started with something from a balanced stochastic block model. How would you estimate that in the unbalanced case? And then it would be interesting to have more instances of this meta claim that if you have more signal, then you can solve your clustering problem faster. Okay, so that concludes a portion of the talk on clusters. We're now going to talk about manifolds. And this is work that I've done with Jameson.
Quick question.
Yeah.
Are there any other properties that you're ensuring about the subgraph that you're sketching down to? I'm assuming it has to at least be connected, or the sizes are, you're really just randomly selecting and running with whatever you get.
That's correct. So with low probability, the algorithm breaks.
Okay.
But with high probability, we win all the way.
I got it. Okay, so that's built into your success, sort of your theoretical recovery guarantee.
Yep.
Okay. All right. Thanks.
Sure thing. Great. So manifolds. This is. Okay.
Can I ask a question?
Please.
Yes.
So in the setting from Afonso's paper, you needed that the degree was not constant, something like alpha is not a constant, but scales like log n or something like that. Do you get something like this in your
so our log n
result?
So we have this scaling right here. Maybe that's what you're talking about.
Yeah. Oh, okay. Yeah. Sorry, I missed.
So we're using the same regime that Afonso was thinking about. Mm-hmm.
So then, if you sample a constant fraction of points, then you still have that is unlikely to be disconnected or something like that.
Yes.
Thanks.
I also have a question following up on what Soledad asked. Is the proof of the statement you have, is it done with matrix Bernstein? The 16 over 3?
Yes, that's where
those numbers look familiar.
Yeah, that's where that comes from.
And your conjecture, is it based on the fact that at this point you start having the property that if you know everyone's membership except one, you would be able to tell who that belongs to? So is that where this conjecture is coming from? Or
this
no?
conjecture is not coming from thoughts so much as it's coming from empirics. Like we observe this behavior. And it would be interesting to follow through with theorems. Presumably, we'd have to open up what you did with matrix Laplacians or whatever, random Laplacians.
Yeah, but if what I just said is true for this threshold, then it might work. Yeah, thanks.
Sure. So manifolds, here we go. Joint work with Jameson Cahill and Hans Parshall. I want to start with a toy picture. So symmetry and machine learning. Let's say we have data of this form, and we're interested in classifying. So just by looking at this, you'll note that there's symmetry exhibited by this data. There's this rotational symmetry, and you can pass to invariance under this symmetry in order to simplify your classification task. So in this case, the distance from the vertical axis as well as this z coordinate, these two things provide a complete invariant to this symmetry. And you could imagine training your classification algorithm in this invariant feature space. And certainly it would be a lot easier to train a classifier in the invariant space than it would be to train from the raw data space. Okay, so the symmetry is helping us. This sort of idea implicitly is happening whenever you run principal component analysis. You're using variance in the data to tell you which directions are inconsequential. So you're modding out by shifts in these lower variance directions. For linear discriminant analysis, you're actually using the label to inform what directions you should be modding out by. So these affine symmetries are somehow being learned by PCA and LDA. More modern techniques, specifically for images, actually impose side information about the symmetry group. Like it exploits that images tend to be closed under elastic distortions and in particular translations. So you can exploit these priors in order to do amazing things. For example, you can take your training set and make it bigger by applying elastic distortions to members of your training set. So here's a 6 in the training set, and you apply an elastic distortion to that to produce another 6. It looks like a 6 to me, but maybe that 6 wasn't in your original training set. So you're getting more information for free. The translations are actually baked into architectures of neural nets that are used to classify images. So the convolutional structure is exploiting this translation invariance. I would be interested in having a method that doesn't require a human to tell the computer what the symmetries are. Is there a way for the computer to identify the symmetries just from the training set? That would be interesting. So in order to express this as a math problem, let's think of this setting. We have an unknown distribution that's supported on an unknown manifold. We receive a sample of points according to that distribution, and our task is to estimate the distribution. This is called density estimation. So the standard method for density estimation is called kernel density estimation. What you do is you take a random member of the sample, and then you add Gaussian with covariance determined by the data set, and you see what happens. And this is what, so if this is your training set, it's just 30 samples. This is what a standard kernel density estimation would deliver. This is not using the information that the unknown distribution is supported on a manifold. If you wanted to leverage that prior, you might pass to local PCA to learn approximations of tangent spaces at various points. And this is the result of doing that. It's better, but it still leaves room for improvement. Both of these methods are known to perform really well when the number of samples is large. But as you can see, the performance is not so great in this setting where the number of samples is small, these 30 samples right here. But ingredients matter. If you have an informative prior, and we're going to have an informative prior more than just the manifold structure. If you have an informative prior, that'll allow you to get away with fewer samples. So for us, we're going to be interested in manifolds that have a large symmetry group. We're not going to know what the symmetry group is, but we're going to know that it has a symmetry group, whatever it is, okay? So the symmetry group here is going to be all members of GL that the manifold is invariant under, okay? GL, I'm not saying orthogonal. It's not the orthogonal group. It's the general linear group, invertible matrices. All invertible matrices that the manifold is invariant under. Okay, so the Lie algebra is going to be you could think of it as a vector space of matrices. It's the tangent space of this symmetry group at the identity. So you're probably, I don't know if you're familiar with this font. It's MathFrac or Fraktur. That's an SYM, the same SYM as in symmetry, but it's in this MathFrac font. It's traditional to denote Lie algebras using that font, so that's what we're doing. Okay, so suppose that a genie told us what the Lie algebra is of the symmetry group. Then you could do a decent job of estimating the distribution. The way you would do it is you'd randomly draw a point from your sample, and then you would randomly draw a matrix from the Lie algebra. And what that matrix in the Lie algebra is doing is it is giving you instructions for how to deform that sample that you drew. So in particular, you apply the matrix exponential to this member of the Lie algebra. That's going to give you a member of the symmetry group that's close to the identity. And then you apply that, that group element to X. And that's going to give you a slight deformation, kind of like an elastic distortion of a 6. But you're using the Lie algebra that's given to you. So this reduces our problem to estimating the Lie algebra from the data set. And that's what we're interested in doing. So the way we accomplish this is with this lemma. This lemma is very easy to prove, but it's very important for us. So I want you to pay close attention right now. So if you have a member of the manifold and a member of the Lie algebra of the symmetry group of that manifold, it's always going to be the case that that matrix applied to that vector is going to reside in the tangent space of the manifold at that vector. Okay? So we have access to members of the manifold. This is our sample. If you run local PCA, you can obtain estimates of the corresponding tangent spaces. And X combined with that tangent space is giving you information about all members of the Lie algebra you're looking for. So in particular, you can run local PCA to get these estimates of the tangent space, and then ask for all matrices that have the property that matrix applied to the ith sample resides in the ith tangent space for each I. Okay, these are linear constraints on the matrices A. And intuitively, if you have enough of these constraints, then it's going to identify the Lie algebra you're looking for. Okay. Now, when you run local PCA, you're not getting the exact tangent space. You're getting an estimate of it. So, and this is rather brittle when it comes to these approximations. So for a more robust version, you solve a, you pass to a spectral problem. So we'll let SI denote the vector space of matrices that are consistent with XI and TI. And then we're going to think about orthogonal projection onto the orthogonal complement of these spaces. We're going to add them up, and it's not difficult to see that the bottom eigenvectors of this matrix will span an approximation to the desired Lie algebra, provided you have enough samples and they're sufficiently different. You need diversity of data. Okay. It works. So these are some experiments using different manifolds. So this is a training set of points drawn from the line. These are points from the ellipse. This is actually the same collection of points we had earlier when we ran those alternative methods. These are points on a hyperbola. These are points on an ellipse, but then we added noise to mess it up. And then these are points on a torus. So if you look at what Lie PCA produces, you end up with point sets that don't look that different from what the test set produces. Both of these are like 300 samples. This from an estimated distribution, this from the true distribution. I want to point out that this picture right here of Lie PCA acting on ellipse plus noise, what you're seeing is artifacts of our technique where we draw one of these samples at random, and then we apply e to the a being a member of the estimated Lie algebra. You can kind of see little trajectories from these samples. Kind of looks like a galaxy. So the optics are good. It looks like it's doing well. You can actually quantify how well it's doing by looking at different metrics between the 300 points that Lie PCA produces and the 300 points that the test set has. You can take the Earth movers distance or the Hausdorff distance and look at numbers and make comparisons, and consistently Lie PCA is outperforming the competition. I'm interested in proving theorems. I told you that you can expect to require fewer samples in order to run Lie PCA. For these theorems, we're going to have Ti be the exact tangent space at xi, not just an approximation, it's exact. So you receive points on the manifold and exactly the corresponding tangent spaces for these results. So a simple result, just a simple dimension count, tells you that you're going to exactly recover the Lie algebra only if you have enough samples. So this is a lower bound on the sample complexity necessary. We're going to call this n star. N star of the manifold is this threshold you need to surpass in order to win. And what he is a quotient of codimensions. So we have the codimension of the Lie algebra as a subspace of D by D matrices, and then the codimension of the manifold as a submanifold of RD. And when you work out what codimension means and what this quotient is doing, what we're getting is that it's better to have a lower dimensional manifold, and it's also better to have more symmetries. And that kind of matches our intuition. But this is just a lower bound. We're actually interested in the honest sample complexity. And what we were able to do is solve this problem for particular manifolds. So for particular examples of manifolds, you can actually show that a generic sample from the manifold of size equal to n star will allow you to win. It would be interesting to characterize the manifolds that have this property. And in fact, that's one of our open problems. We'd also be interested in figuring out how to round to a nearby Lie algebra. So our spectral method can be thought of as a spectral relaxation of the thing that you actually want to solve. You want to find the best Lie algebra that fits your data, and you relax to the Grassmannian. So you're just asking for a subspace of matrices instead. But a Lie algebra is going to have additional, well, it has algebraic structure. There's a bracket, and we're ignoring that bracket. It would be interesting if we could systematically round to a nearby Lie algebra. It's unclear what the right way to draw A randomly from the Lie algebra is. That's a thing that we do in our density estimation. And what we did was we applied some ad hoc version of what they do for kernel density estimation. We just transferred the moves that they do over to our setting, but we haven't seriously analyzed the right way to do that. And finally, there's an interesting thing where if the symmetry group doesn't act transitively on the manifold, then the Lie algebra is not giving you the full picture. So an example would be the torus, where the symmetry group has orbits that are just these circles along the edge of the torus. So the Lie algebra would be shifting you along those circles, and those trajectories aren't filling out the full dimensionality of the torus. So we could imagine exploiting more information from local PCA to allow us to peruse that dimensionality, but that would require a modification of our algorithm. So that concludes the manifolds portion of this talk. And the last portion is about...
So Dustin, I'm going to interrupt real fast. And you might have actually answered this at the very end, but I was distracted for a moment. So you're assuming here in this model that you know the underlying dimension of the data manifold?
We're assuming so much. We're assuming we know in order to run our algorithm, we need to guess the dimension of the manifold in order to run local PCA. We also need to guess the dimension of the Lie algebra in order to run that spectral method. So these are hyperparameters that that need to be sorted out as part of the algorithm as well. So maybe there's some sort of elbow rule of thumb that you could use, but yeah, we haven't tackled that part of the problem.
So I just wanted to mention you could almost think of this as like a persistence PCA that Maggioni and some others worked on. They call it geometric multi-resolution analysis. But the idea is that you kind of have a system of nested decompositions of your data points, and then you do local PCA and you sort of track the changes and track how the singular values change. And it gives you a sort of estimate then, like what are the persistent significant singular values when you're doing the local PCA, and that gives you an estimate of the actual inherent dimensionality of your noise you draw from a manifold.
Yeah, that might be a more systematic way of picking those hyperparameters. That's nice. Great.
I was a bit confused about your mention of affine spaces. So don't you require your manifold to be compact? And then I don't know why an affine space in general would be invariant under multiplications by non-singular matrices.
So an example of a non-compact manifold would be a line, for example.
You don't
and
require to be compact in.
I'm sorry?
In your theory, you don't require the manifold to be compact?
No. Yeah, so you might wonder, what does it mean to be a generic sample? And what that means is it resides in a open, dense subspace of m to the n, so n copies of m, like Cartesian product with itself, n times. So we don't require knowledge of the distribution in order to have this theorem. And yeah, we don't require compactness. So affine subspaces, quadrics like a hyperboloid are good for this theorem.
Thank you.
Sure thing. Anything else? Great. Part 3, epidemics. You're doing great, guys. We just have 15 minutes left, so just hang in there. This is joint work with my math PhD student, Charles Clum. I'm pretty excited about this. So the goal is to have an informative forecast of an epidemic, and you want it as early as possible, okay? You want to know what the curve looks like that you're trying to flatten, and that will inform how the public ought to respond. And it could even save lives, okay? We want an early and informative forecast. So let me tell you about what they did for COVID-19. So this figure comes from a paper in the New England Journal of Medicine. What they did was they took the data from COVID-19 in Wuhan, China, and they identified what did they have access to? They had access to who got infected and when, and then they did some detective work to identify the social network. And in particular, they managed to deduce certain examples of this person definitely infected that person. And they had 5 clusters of this form where this person got infected on one day, and then 5 days later, they infected this person, who in turn 4 days later infected that person. And it was this data set, it's pretty small. This data set is what they used to estimate the rate at which COVID-19 was spreading. And that informed policy, right? So what I'm interested in is whether one could design a principled algorithm for estimating this rate of spread, and furthermore, whether you can get performance guarantees for such an algorithm. So we're going to be thinking in the context of a really popular model for epidemics. This is the SIR model. S stands for susceptible, I stands for infected, R stands for recovered, okay? So you have a social network, G. It consists of vertices and edges. And what we're going to be looking at is an evolution of a partition of the vertex set. You have susceptible vertices, you have infected vertices, you have recovered vertices. And that evolution is going to follow a continuous time Markov chain, CTMC, okay? Let me tell you how that Markov chain goes. So you initialize by drawing a vertex uniformly at random from the vertex set. And you're going to say that that vertex is infected, and all of the other vertices are going to be susceptible. No one's recovered just yet. This is the initial condition. And from that point forward, you will be evolving according to certain transitions. These transitions are determined by 2 fundamental parameters. These are the parameters that we want to estimate. One stands for the infection rate, and the other stands for the recovery rate. So for at any time, every susceptible vertex is going to become infected at a rate proportional to the number of neighbors that are infected. So if you have more infected neighbors, you're going to get infected faster. And then for every infected person, they're going to become recovered at a rate of mu. So mu is basically the like biology running its course. How long does it take for you to get over it? That's the model, okay? So a common simplification of this model is to take your social network to be the complete graph. And when doing this, it's convenient to think of not lambda, but n times lambda. They call that beta. So when n is large, you can take the mean field approximation of your continuous time Markov chain, and it reduces it to a system of ordinary differential equations that are a lot easier to solve. And this is an example of a solution to that. You see that this is the curve of infected people. This is the curve that we want to flatten. And if you know beta and mu, you can run this model and see what the curve is going to look like. But suppose what's actually happening is we're observing this curve over time, and we want to figure out what the parameters are. So it turns out that for small values of time, the curve looks like an exponential, and the rate is beta minus mu. Okay, so you can plot the data in log scale and take the slope, and that's going to give you an estimate of beta minus mu. But it's not going to tell you what beta and mu are. It's going to tell you that beta minus mu equals something. You have 2 variables, but only 1 constraint. Sadly, the thing you actually care about, which is the peak, this is actually determined not by the difference of beta and mu, but rather the quotient of beta and mu. You can argue this by time dilation. So what that means is, for this particular social network, you're not going to be able to identify the SIR parameters, at least before you reach the peak. Once the curve makes a turn, you can do curve fitting to do a decent job of estimating that. But for early times, when you're in the exponential phase of this curve, there's no hope for identifiability. But ingredients matter. In this case, we're going to use data diversity in order to get identifiability. The complete graph is bad, and the intuition for it being bad is you can't do what they did for that Wuhan data set. They did detective work to figure out who infected whom. You can't do that with the complete graph because you could have been infected by anyone who's infected, okay? We're gonna operate under the hypothesis that social networks allow you to get this data diversity, in particular by way of controlled infections. Let me tell you what I mean by controlled infection. So I want you to think about a very easy version of the SIR model. Let's say you have a social network of 2 vertices and they're both adjacent to each other, okay? So K2. So one vertex, call it V, is going to be infected at time 0, and then the other vertex will become infected at some random time. That random time will have certain statistics. So the probability that the random time is finite will be lambda over lambda plus mu. The reason is that you have 2 exponential processes competing. It's the exponential process of getting infected versus the exponential process of getting recovered. So if the other vertex infects you before they recover, then your infection time is finite and you end up with this quotient for that probability. Also, if you condition on getting infected, the expected time it takes to get infected will be 1 over lambda plus mu. The reason is that under that conditioning, the infection time is an exponential of rate lambda plus mu because you're competing these 2 things. So we have these, we have P and Q, and notice that if I knew P and Q, I could figure out lambda and mu. In particular, P divided by Q is lambda. That's easy to see. The other one is also easy to get. The big picture of our approach, like the core idea is we're going to identify multiple copies of this simplistic SIR model, that's SIR model on K2. We're going to find multiple copies of that in our social network. These are going to be multiple controlled infections in our social network. And by having a bunch of these at our disposal, we're going to be able to estimate this probability and this expectation. We're going to be able to estimate P and Q. And once we have P and Q, we can estimate lambda and mu. That's the big idea. So a little more of the details of our approach. We're going to have some numbers, R, T naught, and tau. And this is a picture of a social network, say, okay? And we have patient 0. Patient 0 is in red here. We're going to, once patient 0 emerges, we're going to look at a subgraph induced by vertices that are at most R away from patient 0. So in this picture, R equals 4, okay? That's what H is. We're gonna use H to do a thing. The infection is spreading. So the red vertices here are the guys that have been infected at some time before T naught, okay? That's what T naught is governing. Once I have that information, I can hunt for bridges in H. So bridges in the green graph, these are edges whose deletion would increase the number of connected components in H, okay? We want bridges that are disjoint, so they don't touch the same vertices, and they're gonna have a single vertex in this red subgraph. The other vertex is going to be in green. These are our controlled infections. And now we're going to monitor how the infection traverses along these bridges in order to get the statistics we need to estimate lambda and mu. So T is the infection time it takes to go across the bridge. Z, we're going to be truncating that against tau because we don't want to have to wait forever to get our estimate. Remember, we want to estimate things in a short amount of time. So we do a truncation, we incur a little bit of error from that, but then we end up estimating P and Q, and then we smash those together to estimate lambda and mu, and that's what we output, is lambda hat and mu hat. This method works. So imagine running the SIR model on an infinite d-ary tree. Okay, so you have a root node, and then each node has d descendants, or d children. So we're going to focus on mu being 1, because we can assume that by time dilation. And we're going to take parameters to be this. The most interesting one here is T naught. So we pick T naught to be how long it takes for 100 people to get infected. And the reason we do that is because we wanted to have enough bridges in order to average out and get decent estimates for P and Q. Okay, and I'm going to show you 2 charts here. This first chart is it's telling you what's the probability that you actually end up with 100 infections. So it could be that the infection stops spreading quickly. This is actually good news, but it's bad for our algorithm. So there's 2 regimes here. There's a dichotomy. There's when things are good for the people, and then there's where things are good for the algorithm to perform the estimation. So here, darker is better for the people, and lighter means that you have data available to actually run the algorithm. Over here, it tells you how good the algorithm is performing. Lighter is better. We have X's on some of these pixels because there wasn't enough information to run our algorithm. So we just, there's nothing to report in those cases. But you can see that we perform better when lambda is bigger and when D is bigger. It kind of mimics the phase transition for when the infection dies out on its own. Okay, and that kind of informed how we find a performance guarantee. So we can prove theorems about regular locally tree-like graphs. So you should think that if you draw a regular graph at random, it's going to be locally tree-like with high probability. And if you have a regular locally tree-like graph, what you can do is, well, you can prove this theorem. I'll tell you how the ingredients later. So the content is if the lambda parameter is at least something times the mu parameter, in this case 6, then you have this dichotomy. Either there's no epidemic or the algorithm works. In particular, we can guarantee that lambda and mu are both within a factor of 8 of the true lambda and mu with high probability. And these are artifacts of our proof strategy. So we think that 6 can be replaced with 1 over d minus 2. And similarly, we think 8 can be replaced by some constant that goes to 1 as the degree goes to infinity. The proof ingredients is we open up the literature on SIR dynamics on infinite d-ary trees. If you're locally tree-like, then you can exploit this literature to your benefit. And you take what they know and you massage it to be of the form that you need for your algorithm, and to analyze that performance, you pass to Bernstein's inequality. So go to Verschinen's book for details. But to get from the literature to the guarantees, you have to do a lot of annoying analysis, lots of conditioning games, because in order to deal with the dichotomy, remember, we said conditioned on a fraction of vertices getting infected. So that conditioning meant that we had to move events around in order to pass from the literature to the guarantee. And that was not terribly fun. Great. Lots of open problems. We'd like the 6 and the 8 in our performance guarantees to be improved. It would be interesting to understand fundamental limits of early time identifiability. We saw that the complete graph was bad. What does it mean to be bad in general? What are the combinatorial features that mean that you're bad? other estimators like maximum likelihood. We focused on locally tree-like graphs because that's the literature allowed us to analyze that more readily. It'd be interesting to look at other graph families like small world networks. Other models, we focused on the SIR model. Also, there's a different model for what your data could be. If you have asymptomatic spread, then you're not going to know the entire infected set. So it would be interesting to see what you can say when you have that arm tied behind your back. Overall, ingredients matter. We talked about clusters, manifolds, and epidemics. I showed you lots of open problems. And if you took anything away from this talk, please don't eat rotten tomatoes. Okay, that was a joke. I don't want you to take it seriously. Please don't eat rotten tomatoes. Everything I talked about was posted on the archive on Tuesday, and you can check it out. And that concludes my talk.
All right, thanks a lot for an excellent talk. I will stop recording now and invite any